Good afternoon, everyone. In this joint work with Amor Keziou, we have been interested in independence testing based on generalized mutual information in a semi-parametric context. So here are the outlines of my talk. I will start with a short introduction on independence testing and try to motivate the use of mutual informations in this context. I then will present the semi-parametric model under study. I will present the estimation strategy based on this semi-parametric modeling and the dual representation of phi mutual information. I will give the good asymptotic properties of these estimators for the mutual informations, from which we will be able to build explicit critical regions for the independence tests. And then I'll compare the obtained tests in terms of their Bahadur asymptotic efficiency and will illustrate their behavior through simulations. Okay, when talking about independence test, I think the first method that comes into mind to people is the chi-square independence test, which is based on the chi-square dependence measure, which is defined in the following way and takes this form for finite random variables. But you can also consider as an alternative the test based on the mutual information, that is the dependence measure that you obtain considering the Kullback-Leibler divergence between the joint distribution of the couple of random variables and the product of the marginal distribution. Okay, when you're dealing with finite random variables, you can easily estimate both of these quantities just by plugging the empirical counterparts of the joint distribution and the product of the marginals into the related divergence. And you obtain, the classical chi-square test statistics for independence, as well as the classical Kullback-Leibler independence test statistics, which are well known to be asymptotically chi-square distributed under the null hypothesis of independence. So you are able to compute the p-values using this approximation. Okay, we could consider other dependence measures. For example, considering phi mutual informations between the joint distribution and the product of the marginals. And then, in the same way, for finite random variables, estimate empirically the joint distribution and the product of the marginals, and get, again, a test statistics which will be chi-squared distributed asymptotically. Okay, the main fact here is that this phi mutual information is positive and is null if and only if the random variables are independent. And so the test problematic here can be reformulated into does the phi mutual information equals 0 or not? Okay, so as I said, for finite random variables, it's quite easy to implement. But what if you deal with general random variables, or at least with continuous random variables? Well, you cannot just consider as an estimator of the mutual information the empirical one, that is the one obtained by plugging the empirical distribution, because it will be degenerated and you will reject the null hypothesis without reason. Okay, I think there are two main approaches for for continuous random variables. First, you can discretize your your continuous observations, and then apply the previous methodology to the discretized observations. Of course, this yields to poor efficiency because you lose a lot of information from the continuous observation to the discrete one. And there are intrinsic technical difficulties, such as choosing the number of classes and choosing the classes as well. Another approach consists in estimating the density of the distributions using kernel estimation. But again, you have difficulties intrinsic to this approach, because you have to choose the kernel, to choose the bandwidth, and even if you have good choices for both of them, the asymptotic distribution of the estimators may remain unknown. And so you cannot use this asymptotic distribution to get explicit critical region. Okay, so here we have developed an alternative approach for general random couples by considering a semi-parametric model on the distribution of the couple. Namely, we consider the set of all distributions such that the density ratio of the joint distribution with respect to its marginals belongs to some parametric set of functions. So here we have nothing to know about the marginal distribution, but just on the ratio between the joint distribution and its marginals. Okay, so this kind of modeling is sufficiently large to cover a large variety of situations, including the two-dimensional Gaussian model, because in this case you can easily prove that the density ratio is the exponential of polynomial function of degree 2. And so you can embed the Gaussian model into some semi-parametric model as described here. Okay, so it covers the Gaussian case. It covers also the finite random variables case, because again you can represent the density ratio between the joint distribution and its marginals as the form expected in the model. And more generally, you can consider for the set of parametric function h theta any parametric copula model, okay, which is the exact sense of our semi-parametric model, since you are interested here just in the ratio between the joint distribution and its marginal, which is typically the definition for copula models. Okay, so now how to take advantage of this semi-parametric modeling to efficiently estimate the mutual information. Well, we will take advantage of the following dual representation for phi divergence. Namely, any phi divergence between a probability distribution Q, which is absolutely continuous with respect to another one P, can be expressed as a supremum of an objective function given here, which is the sum of two integral terms. The first one computed with respect to the Q distribution, and the second one with respect to P. And the supremum is taken over a set of functions which contains the functions that realize the supremum, namely the derivative of phi evaluated into the density ratio between Q and P. So if we particularize this result in the context of mutual information, and taking advantage of our modeling, we obtain that under some integrability conditions on the model, the phi mutual information can be expressed as a supremum on the set of parameters of this objective function, which again is the sum of two integral terms. The first one computed with respect to the joint distribution, and the second one with respect to the product of the marginal distribution. And the supremum is achieved for the true parameter of the joint distribution. Okay. So the advantage of this dual formula is that when you plug the empirical counterparts of the joint distribution and the marginal, then you obtain something that is, you can then compute the supremum, and you obtain something that is not degenerated as previously. So explicitly, when your observations are an n sample of a couple of random variables drawn according to some probability p, and that you assume that the density ratio belongs to this semi-parametric model, then we call the dual estimator of the phi mutual information the estimator obtained by computing the supremum over the set of parameters of this empirical version of the objective function. And you can also estimate in the same way the parameter of the associated to the joint distribution. Okay, just observe that this estimation strategy recovers the empirical strategy when you are considering the finite distribution model. Precisely, we can, well, the dual estimator equals the empirical one in this context, and so you can you obtain again the classic chi-square estimate if you take the appropriate phi function. And so this methodology recovers particularly the chi-square independence tests. Okay, for the copula models, well, the marginal cumulative density functions are unknown, so you have to estimate them. And the result is that the phi mutual information, the dual estimator of the phi mutual information depends on the rank statistics associated to the sample, but you can still estimate it quite easily and obtain estimators with good asymptotic properties that I will present now. Okay, so you have to add some integrability and regularity conditions on the model, which are quite classical in M estimation theory. And under these assumptions on the model, you obtain that the dual estimators of the phi mutual information is consistent, that is, it converges to the true value of the phi mutual of the joint distribution. Okay, so it is consistent, but in the aim of independence testing, you have to know the distribution of the test statistics. So adding additional assumption on the model, you can explicit the asymptotic distribution of the test statistics. It depends on the phi function that you are considering. Precisely, I will present the results for the classical Kullback-Leibler mutual information. You have to assume that the model essentially is exponential with is an exponential family with separated values for the the functions inside the exponential family. Okay, so for that kind of model, and under the classical assumptions of regularity and differentiability, we can explicit the asymptotic distribution of the dual estimator of the Kullback-Leibler mutual information. Precisely, it converges to a non-central chi-square distribution with the rate 1/2n. So if you are interested with other phi mutual information, you have to consider as model, instead of the exponential function, you have to consider the inverse of the derivative of the function phi. But you can still obtain an asymptotic distribution. Okay, so now we are able to use this asymptotic distribution to compute the critical values for the test associated to this phi mutual informations. The question remaining is, what is the test I have to choose in all this family of tests? A piece of response is the following theorem that states the most efficient test among all mutual information-based tests is the one based on the Kullback-Leibler mutual information, the classical one, in terms of Bahadur efficiency. So this result relies on a large deviation principle for the sequence of the dual estimates for the phi mutual information. I didn't give it here, but you can find it in the paper. Okay, just have a look at some simulation results on this independence test procedure. Precisely here, we consider the case of two random variables, two binary random variables, and we compare the Kullback-Leibler independence test with the chi-square one, and what we obtain for a small significance level is that the Kullback-Leibler independence test is more powerful than the chi-square independence test. Okay. Finally, we have performed also some simulation for Gaussian couples, and we obtained the same kind of result. We have compared the Kullback-Leibler independence test with the chi-square one, with the Pearson test, with the Spearman one, and with Kendall. What we obtain is that Kullback-Leibler test is nearly as powerful as the Pearson test, that is the most efficient one in the context of Gaussian model. Whereas the chi-square test is a bit less powerful and is more comparable to Spearman and Kendall tests for here for a sample of size 50. Okay, we have also performed simulation for FGM copulas and other models that I didn't present here, but you can find it in the full version of the paper that is available on the archive. Okay, so I have finished. Welcome. We didn't look, but I think the first speaker said that it could lack of robustness, so we could have a look at this situation. Yeah. Thank you.